Solving quantified problems and games in polynomial space. We now discuss how to solve all of these problems in polynomial space. As we will see, this will be trickier, in one case a lot trickier, than the simple task we faced in showing that problems like 3-set and independent set belong to MP. We begin here with Q-set and competitive facility location, and then consider planning in the next section. Designing an algorithm for Q-set. First, let's show that Q-set can be solved in polynomial space. As was the case with 3-set, the idea will be to run a brute force algorithm that reuses spaces carefully as the computation proceeds. Here is the basic brute force approach. To deal with the first quantifier, there exists x1, we consider both possible values for x1 in sequence. We first set x1 equals to 0 and see recursively whether the remaining portion of the formula evaluates to 1. We then set x1 equals to 1 and see recursively whether the remaining portion of the formula evaluates to 1. The full formula evaluates to 1 if and only if either of these recursive calls yields a 1. That's simply the definition of there exists quantifier. This is essentially a divide and conquer algorithm which, given an input with n variables, spawns two recursive calls on inputs with n-1 variables each. If we were to save all the work done in both these recursive calls, our space usage f of s of n would satisfy the recurrence s of n, which is less than or equals to 2 times s of n-1 plus p of n, where p of n is a polynomial function. This would result in an exponential bound which is too large. Fortunately, we can perform a simple optimization that greatly reduces the space usage. When we're done with the case x1 equals to 0, all we really need to save is the single bit that represents the outcome of the recursive call. We can throw away all the other intermediate work. This is another example of reuse. We are reusing the space from the computation for x1 equals to 0 in order to compute the case x1 equals to 1. Here is a compact description of the algorithm. If the first quantifier is there exists xi, then set xi equals to 0 and recursively evaluate the quantified expression over the remaining variables. Save the result 0 or 1 and delete all other intermediate work. Set xi equals to 1 and recursively evaluate the quantified expression over the remaining variables. If either outcome yielded an evaluation of 1, then return 1, else return 0. And if the first quantifier is for all xi, then set xi equals to 0 and recursively evaluate the quantified expression over the remaining variables. Save the result 0 or 1 and delete all other intermediate work. Set xi equals to 1 and recursively evaluate the quantified expression over the remaining variables. If both outcomes yielded an evaluation of 1, then return 1, else return 0. And if analyzing the algorithm, since the recursive calls for the cases x1 equals to 0 and x1 equals to 1 overwrite the same space, our space requirement s of n for an n variable problem is simply a polynomial in n plus the space requirement for one recursive call on an n-1 variable problem. That is, s of n is less than or equals to s of n-1 plus p of n, where again p of n is a polynomial function. Unrolling this recurrence, we get s of n is less than or equals to p of n plus p of n-1 plus p of n-2 and so on plus p of 1, which is less than or equals to n times p of n. Since our p of n is polynomial, so is n times p of n, and hence our space usage is polynomial in n as desired. In summary, we have shown the following. 9.4 QSAT can be solved in polynomial space. Extensions, an algorithm for competitive facility location. We can determine which player has a forced win in a game such as competitive facility location by a very similar type of algorithm. Suppose player 1 moves first. We consider all of his possible moves in sequence. For each of these moves, we see who has a forced win in the resulting game, with player 2 moving first. If player 1 has a forced win in any of them, that player 1 has a first win from the initial position. The crucial point, as in the QSET algorithm, is that we can reuse the space from one candidate move to the next. We need only store the single bit representing the outcome. In this way, we only consume a polynomial amount of space plus the space requirement for one recursive call on a graph with fewer nodes. As in the case of QSET, we get the recurrence s of n is less than or equals to s of n minus 1 plus p of n for a polynomial p of n. In summary, we have shown the following. 9.5. Competitive facility location can be solved in polynomial space.